Hello there! In this video, we'll be learning about continuity over an interval. So far, we know that a function f is continuous at a point x equals a if and only if the three-step test is satisfied. Or in summary of this test, the limit of f as x goes to a is equal to its function value at a. How about for an interval, say the open interval AB? How do we determine that this is true? Well, given continuity at a point, we can determine the continuity at an interval by checking if f is continuous over every point in the interval AB. So makes sense, since if it is continuous at every point in AB, in the interval AB, then it follows that it is continuous at the whole interval. But it might seem scary, since if we need to check every point, then we need to keep repeating this process. But actually that isn't the case, since by using the graphs, we can easily see if f is continuous over every point in that interval. So we'll utilize the graphs later on. Aside from this, we might also ask, how about for the closed interval AB? Well, the technique to check this is to check if f is continuous on the open interval AB plus checking if f is continuous from the right of A. So this one out here represents this part, continuous from the right of A, and if f is continuous from the left of B to represent this part. So these two are what we'll be dealing with in this video. Aside from this, a good question to ask is, how about for these intervals, or intervals that are half open and half closed? How do we determine its continuity? So you may pause the video for a while to think about this. Okay, good. So when dealing with these intervals, take note that for this one out here, the thing that we'll remove is this part out here. Since if we remove this one, then we have the open interval plus the bound out here. So this one again represents this part out, plus this one to obtain this. So it's something like that. Okay, good. So to understand these concepts much better, we'll have an example or an illustration. So let's have this graph out here. So it's quite complex and quite scary, but we can work on this one. We'll start by focusing on this curve of the graph first. Okay, so let's start. Let's try to check or consider the interval, the open interval, -9, -7. So this is this part out here. And the technique to check if the function is continuous at a certain interval is if we can draw a line out here without even lifting our pencil or pen up. And as you can see, we were able to do that in this interval. So we can see that this interval out here, or the function, is continuous at this interval, since there are no holes and there are no gaps. How about for the closed interval? Well, the process is the same, but we consider this point out here. So we draw this one, this line. Clearly again, there are no cuts and holes. Aside from this, clearly the limit from the left of this bound approaches the actual function value, and from the right, it clearly approaches the function value. So we'll have no problems again, and we can say that f is continuous at this interval. How about for the open interval -9, -6? So we are dealing with this and this part. Again, if we try to draw a line, we won't have any problems. You might think that we have a problem since there is a hole here. But since we're dealing with an open interval, we know that the bounds are not included. So -6 is not present in this interval. So to correct this one, it's only around here. So again, we won't have any problems out here. So we can say that f is continuous at this open interval. But how about for the closed interval, -9, -6? So it will be this one up until this part out here. So if we draw a line out here, clearly we'll have problems since we'll reach the point -6. So -6 is already included out here. Indeed, if we check the limit as x approaches this bound from the right, we'll have no problems there. But from the left of -6 out here, we'll have problems since the limit approaches this point, but the function value is at this point. So we'll have a problem from on the limit from the left of -6. So this closed interval out here, this one, f is discontinuous out there. And for this curve, take note that its continuity occurs on the interval -∞ to -6. Since we can't include -6, but other than that, there are no problems in this graph or this curve out here, since there are no holes and no cuts. So we'll have this. That's it for the first curve on this function. Let's move on to the next one. So this one. And let's consider this interval, the open interval -6 to -3. Again, to check if f is continuous at this interval, so check this one. And observe that we can draw a line out here without any problem. Again, even though there is a hole on -3, -3 is not present in this interval since the bounds of an open interval is not included. So we say that for this interval, f is continuous here. How about for the closed interval -6 to -3? So we'll consider this. If we start by checking the open interval out here, we know from a while ago that it is continuous. Checking the limit from the right of this bound out here, we'll have no problems again since the function value is out here. But from the left of this bound out here, we'll have a problem since its function value is out here. So there is a problem. So there is discontinuity out here, and so for this interval, f is discontinuous out here. But how about if we check the half closed and half open interval, -6 to -3? So we'll have this. And again, we won't have any problems drawing a line out here. And from the right of -6, we won't have any problems since the function value is out here. And we don't need to check the continuity from the left of this bound since this is open. And so we won't have any problems in this interval out here. So we say that f is continuous out here. And in fact, for this part of the curve, it is continuous on this point. So this is the interval where this part of the graph is continuous. So we'll have this. And let's now move on to this section of the graph, this part out here, and let's check some intervals. So starting with the interval, the open interval from -3 to 1. So it is -3 is out here and 1. So if we check this open interval, we'll have this. And clearly we won't have any problems since we can draw a line out here without any problems. So we are continuous at this interval. How about for the closed interval -3 to 1? So we'll have this out here, this. Again, we won't have any problems drawing a line out here, so it is continuous on the open interval. And if we check the limit from the right of -3, we won't have any problems since the function value is out here. And from the left of 1, we won't have any problems again since the function value is out here. So we say that f is continuous at this closed interval. And in fact, this is the interval wherein this part of the graph is continuous. So let's have this. How about for the interval 0 to 2? So 0 is out here and 2 is out here. As you can see, if we try to draw a line from this point out here, there will be a cut before we proceed to this part of the graph. So we'll have a problem in this one, since clearly we can't draw a straight line in this from x equals 0 to x equals 2. So we say that f is discontinuous on this interval. How about for the interval 1 to 5? So that is in here to out here. So since we're considering the open interval, so we can draw a line from here up to here. And observe that even though this extends to infinity, we know that there are some values very close to 5 out here, wherein the curve still extends out there. It will just stop when it reaches x equals 5. But again, since this is an open interval, 5 is not present out here. So we won't have any problems at x equals 5 out. And so we can draw a line from here up to there. And so we say that at this interval, f is continuous out here. How about for the closed interval 1 to 5? Again, we can draw a line out here until a value close to 5. So we won't have any problems with the open interval as we had seen earlier out here. But if we check the limit as x approaches 1 from the right, we'll have a problem since the function value is out here. And same for the left. Since we have this one out here, a vertical asymptote, we know that f is undefined at x equals 5. So we'll have a problem when we deal with the limit out here. So this just tells us that f of 5 is undefined. So even though if we have a limit out here, the limit approaches positive infinity, it won't match this one. Sorry for this poor writing, but I hope you got the idea. So f is discontinuous at the closed interval 1 and 5. And for this part of the graph out here, it is continuous at, so this one, the interval 1 to 5. So I hope you got the idea in this one. I hope that I was able to explain it well, since to understand this process, it's not very structured. It's very intuitive, and it's more on the concept and how it works. Since as you can see, there are no steps involved in doing this one. We just try to explore the graph and draw some lines out here, visualize it, and understand what happens in this graph. So as an exercise, you can work on this one out here. To end this, let's have some remarks, some useful remarks. So first, take note that polynomial functions or functions of the form like this are continuous everywhere. Well, clearly, since its domain is all real numbers. Aside from this, second, Rational functions are continuous everywhere, except at values that would make denominator 0, since we know that in rational functions, it is of the form f of x equals p of x over q of x, wherein q of x is not equal to 0. Since when this is 0, we'll have a value that is undefined. So remove that one, and the rational function is continuous everywhere. Aside from this, what functions do we know? Well, we know the square root function. So consider this square root function, the basic square root function. And we know that this is continuous on 0 to infinity only, since the graph of this function is given by this. So as you can see, 0 included, this is its graph, and so clearly if we draw a line out here, so extend to infinity, we won't have any problems except at values that would make this function negative. So take note that it's important to include 0 out here. So this one is a closed bracket, since we know that there is a value at f of 0, and that is 0. So if we take the limit as x approaches 0 from the right of f of x, we know that this will also be 0. So this one is equal, and so clearly this one is included. For the fourth one, we have the absolute value function. So this is something that we also know, and this one is continuous everywhere, since we know that the graph of f, the absolute value, is given by this out here. So this extends to infinity. So even though there's a cut around here, or not really a cut, but there's like a sudden shift, it is still continuous since there is no stoppage. So we can draw that one without lifting the pencil up. And lastly, so for the fifth one, we know that we discussed the greatest integer function. Take note that the greatest integer function is continuous on this interval. So this interval was obtained, and since we know that the greatest integer function of x is equal to n if x is from n, including n, to n plus 1. Since if we try to recall, its graph is like it's given by this, and this like that. So it is continuous like on 0 to 1, then on 1 to 2, then 2 to 3, and so on. So like that. So yeah, that's it. So it's quite a long video, but I hope you now have a better understanding on how continuity over an interval works. So if this video is quite difficult to comprehend, you may check out other resources, especially on the Khan Academy video. It's really helpful. So yeah, I hope you enjoyed this one, and feel free to comment down below if you have any suggestions and recommendations for this video, this playlist, and this channel in general. So yeah, that's it, and that's all for this video.